Good day, everyone. Today we'll move on our discussion on robot control systems, and we'll finally talk about control. So we'll talk a little bit about control theory in general to remember what you did in systems theory. Pleasant times, from what I know. And then we'll see two different approaches to actually controlling a robot arm. What we call the independent joint control and the computed joint control. Basically what we did until now was modeling. We did kinematics, inverse, forward, velocities and so on. And last week we did dynamic model, where we saw how forces come into play. And today we'll talk about how do we control this robot. So basically we need to consider the robot as a process based on what you already learned in system theory, where you had some process that we were trying to control, and you would write a transfer function, or I don't know how you dealt with the problem, and you design a controller to make that process do something, right? So you had this kind of block diagrams, if I'm not mistaken, where you have a process. This is, I put it here with P. Some kind of response, so something you're reading from the process, some reference or set point, so what did you want the process to do, controller and an action, right? So this is like a simple closed loop a process with a feedback, as I have it here. So in our case, what is the process? What are we trying to control? Say we have the robot and we want to do one of the trajectories we talked about in the past, or something along these lines. What would be the process?
Maybe we are trying to control position, or maybe the force.
All right.
Maybe the velocity of it.
Okay. So then the process would be moving. The robot itself. Or the motors, yeah, because that's actually the part that we're actually controlling, right? The motors, that's where we're interacting. Okay. We'll see about that. It's something in between. What would be a set point? If we say, okay, the process is the motor joints, right? So each one of these independently. What would be a set point? What kind of a thing, or
maybe the
base.
The angle.
The what? The pace?
The base of the robot.
The pace.
Like the reference.
The base. Yeah. I don't hear the word, but base or pace?
Base.
Base. Okay. Right. The base. A velocity. Right. It should be something related to the joint. It could be also the position of the joint. So where is it? Right, so that would be my reference. I want to be at what angle, or it can be velocity. We're talking about velocity control. Then in that case, what would be the response?
The actual movement, let's perform.
The actual movement, or what we measure from the movement?
What we measure.
Right. Okay. Because we will have some. How do we measure the movement? Some encoder or some kind of sensor anyway that measures position, velocity, forces, whatever we're controlling. Right. What are we actually sending to the robot?
Signals.
To the joint, sorry. Current, voltage. Yeah, so some kind of signal to the robot. And what is the controller? We'll see today. All right. So the process we're controlling in the end is not just one joint, because we have like a collection of joints that work together, right? And in the end is what we discussed last week, right? You remember that this was the dynamic model that we defined last week, towards the end of the lecture, and we rushed things a little bit. It's basically something like this, where it shows me what? It shows me for a given acceleration, velocity, and position, of the joints, what is the input torque? And this is what we call the inverse dynamics. We discussed about this concept also in the lab, right? And this is basically a process. This is, what is this actually? This is one equation. This is the set of equations, a system of equations, right? That's what we saw last week, right? It's a system of equations because these entities here are matrices, right? C and D are matrices. G and tau and Q dot are vectors. So basically this is a system of equations, differential equations. That's why we have the dots here, because these are differentials of time, of position and the first derivative of position and the second derivative of position. And this is basically my process. This is, what I'm trying to control. Is this the real process? Or is it something else? So is this actually the robot I'm controlling? How did we call this last week? Dynamic model, right? So I'm trying to get here. This is not the actual robot, it's a model of the robot. So we made some assumptions to build these equations, right? Namely, okay, what is the potential? If you remember, we said we assume there's no deformations. We didn't take into consideration any frictional forces or other kind of effects. And we ended up with this system of equations, which is basically a model of the real process. All right, and we see why this is important later on. All right. So we saw different ideas we had here of what the set point and the response can be, right? We said it can be joint positions, joint velocities, right? But in the end, what do I want to control? Do I care about controlling the joint positions itself? I care about the end effector, right? So can I have like a set point as being the end effector pose and the response being the measurement of the pose? Basically, these two things have to be the same quantity, the same physical measurement. Like the set point and the reference, the reference is the set point, and the response have to be kind of the same thing. So if the set point is joint positions, then I will read here the joint positions so that I compare them, right? If the set point is joint velocities, then I will read here velocity. So can the set point be end effector pose and the response being therefore the end effector pose? It can be joint coordinates, right? This would be like the main candidates. Can you think of why one would be better than the other? Or, it would be the same thing as trying to control the end effector pose, in this kind of scheme, or the joint positions.
I think the end effector pose is harder to measure than joint coordinates, because joint coordinates, I think they can be measured with borders.
All right.
And end effector pose, I have to have some system that can tell me the pose in 3D space.
Which we know. How do we do it? Forward kinematic, right? Okay. Right. If I know joint coordinates, I know where the end effector is. All right. So you're saying that this end effector control directly, having the response, the end effector, and the set point, the end effector pose would be complicated. Why? Because we cannot measure it directly. I mean, we can if we have an external system with cameras or whatnot. Yes, sure. So that's one part of the problem. The other part of the problem is, so I cannot measure directly end effector pose. Can I control end effector pose directly?
No, we need also to control the base with the joints.
We need to actually control the joints coordinates so that I end up having an end effector position, and that's the inverse kinematics, right? So, the first idea would be, let's try to control the end effector pose here, so response to set point can be end effector pose, but that's not really suitable, because the end effector pose is basically constructed by the individual joint motions, right? So we can either measure or control directly the end effector pose. What should the action be? You said some ideas, current and voltage to the joints. Yes, but in the end, if we have this kind of process, the input to the process is what here? The torque, right? So we need to somehow control the torque. So in this block diagram here, the action should be actually torque, because if this is my process that comes here, you know, that's the input. That's how can I affect the response, which would be joint coordinate, joint velocity, joint acceleration, right? So yeah, indeed, low level, I am going to control voltage and current that goes to the joints, but I have to modulate that so that I end up having certain torque here, right? So if here I have like DC motors, which is typically used in robotics, what would I need to modulate in order to have torque control? What property actually is proportional to the torque, voltage or current? The current, right? So here I say I need torque, but in the end, you know, that's very, very linearly correlated to the current I send to the joints. So, okay, in the end, we can say I control the current I send to the joints, and then I have like a scaling factor that calculates the torque that I actually send to the joints. All right. Now, if this is the set point is joint coordinates, right, and the response is joint coordinates, what kind of controllers could I implement here? So now I know the process, right? I know what the action should be. I know the response. I know the set point. Let's talk about this part. What should be the controller? A PID, right? So that would be like the most basic, robust, you know, studied controller of all the times, PID. All right. What is a PID? I hope everybody knows. It's a controller, takes some input, which is the error. What's the error? Set point. It's like saying a prayer. The input to the PID is the difference between the set point and the reference, right? And then we take that difference and we calculate three parts that we add together afterwards: the proportional, the integral, and the derivative part, the PID. All right. How do we calculate these three parts? The proportional part is basically a gain multiplied by this error. So I have this error of time. I multiplied with a gain, just a number. All right. I have the integral of the error over time, right? That I multiplied with another number, another gain. And then I have the derivative of the error over time that I multiply with another gain, another number, and I add these three together. All right, so if we say that the set point and the response is joint coordinates, and basically this error is the difference between these joint coordinates. Right. How many joint coordinates I have, let's say, on this robot? Give a number. It doesn't have to be correct. Then we have 1, 2, 3, 4, 5, 6, 7. Doesn't matter. Point is more than one, right? So using a PID, can I have basically multiple errors, multiple inputs, multiple set points, and multiple references? Because if I say I'll control its joint, and I read the joint coordinates, I basically have to assume that, you know, I need to have a controller controlling all of them, right? Not just one of them. Can I use a PID to control? Why not?
Because it's single input, single output.
Great. It's a CISO controller. Single input, single output. While in this case, I basically have multiple inputs and multiple outputs. So what do?
Can we apply
For each
One by one.
we did the controller for each one.
All right, so we have one separate controller for each joint. All right, that's one idea.
I was thinking to apply a PID for the end effector and then find the joint coordinates using interesting.
Yes, but we said that the end effector itself is not a single input, single output, because the end effector, let's say if I want to control the trajectory, right, it's not just one set point I have, right? I have the 3 coordinates, the 3 rotations, so I basically have 6 set points, right, 6 references. Even if I could describe it with just one number, I would still need to somehow, measure it, and then, as we said, the response and the set point have to have the same kind of, they have to be of the same type, right? So let's say I can measure the set point. I don't know what would be I can measure the reference. How would I decompose this to a torque, basically, to the joint? That's the problem. All right, like a?
Can it be a state controller?
It can be different types of controllers, yes, indeed, but it doesn't have to be PID. But it has to be basically a MIMO controller. That's what you're trying to say, right? Because we have a MIMO system, then we need a MIMO controller, right? Good. We're gonna do both of these, basically. We're gonna do first what we call the independent joint control, where we design separate PID controllers for each joint. All right? So that's the first idea we had here. So we say, okay, I have multiple joints. My whole process is like multiple input, multiple output. I will just try to split it into multiple single input, single output systems. Right? So the idea is to have basically still the same robot process, but then decompose it to the first joint, the second joint, the nth joint. Right? And then design a PID, PD, whatever flavor we want, a controller for each joint. What do we have here? We have the set point for the first joint. We have the measurement from the first joint. I calculate the error. I calculate the action from the PD controller, and I send it to the robot. Yes?
A question regarding robot process that you separated also Q1 and Q2 the joints. How to separate the action, for example, of the joint 1 from the robot?
The action to join one? Yeah, so basically I have independent control of each joint, right? I can modulate the torque for each joint independently, correct? So I can send different voltages or different currents to each joint. So that's not an issue, because they're physically, they are different entities, and a little wire goes to each one of them, right? And at the same time, I also have different encoders on each joint, so I can measure Q1 and Q2 separately. Right, so that's not an issue. So, I can decompose the joint motion independently and then develop a controller for this motor, for this motor, for this motor, and this motor. Right. But this means basically that I consider each joint to be an independent process, right? So that, this joint moves independently from this joint. All right, is this true? Can I assume that this joint moves independently? Can they move independently?
Because it is applied also, for example, if joint, it makes like a translation. If we move the first joint, for example, it could result in a translation of the other joint.
So you're saying that if I move, let's say, this joint,
Yeah, it could result in a translation.
it would result in a translation of this joint, or the
For the whole.
next joints. Why? Or in what sense? I'm not able to understand, I think, what you're saying.
I don't know, I refer more to the duality. For example, if we move a joint, this is the joint, it moves also the whole.
All right, so that's one example. Let me put again this model, right? So what do we have here? We quickly talked last week that we have the inertia matrix here. We have the Coriolis or centrifugal forces matrix here, and the the gravity vector here. Let's take what you say is a good example. Let's say the gravity term here. So this is, we said it's a vector, right? And basically what this vector tells me is what is the torque that each joint feels due to gravity. So we say this is a vector. This will be G1, G2, Gn. So it has n elements, n is the number of joints. All right, what this vector gives me is basically the torque that each joint would feel or would have to compensate due to gravity. So what does that mean? I have this joint here, and in order to keep the robot straight and fixed in this position, it has to overcome the torque from the gravity. Like these links here have some mass that is being pulled by the earth, right? And this joint has to basically counteract that torque from the gravity, right? This has to do with this mass and the distance from this joint, and this mass and the distance from this joint, and all the subsequent masses and their moments of arm, basically this distance, right? That creates a torque. Right, so I'll have some torque for the first joint, some torque for the second, for the third, and so on and so forth, right? And you see also on the slide, and it makes sense, that these are functions of Q. Right? Why is this a function of Q? Because let's take this joint example, right? So the torque that it has to counteract has to do with how the robot is positioned, right? If this robot is like this, standing up, basically all the masses, the distance from the axis of rotation is very small, so the torques they generate is very small compared to, I don't know, in this situation, you might be able to see that it's actually, no, it doesn't slide down. But here I have the same masses, but over a bigger distance from the axis of rotation, so they generate more torque that this joint has to overcome, right? So that's one simple example of how, let's say, okay, in this example it's just this joint affecting its own joint, but I can have the other joints affecting this joint as well, right? So here again I have the masses further away from the axis of rotation, but I might do something like this, and now the masses are closer, so, or even on the other side, so I might have different torques due to gravity being generated also due to the other joints. Okay, so that's like one example. The position of the joints affects the torques I need to send to all the joints in order to stabilize the robot, right? It's not just the position, it's also the velocities, right? And that's something you haven't seen in the lab, but you will see this week, how this term affects basically the behavior of the robot. So we call this the Coriolis or centrifugal terms. So this has to do with basically how velocity affects the torques generated at some joints. So I'll try to demonstrate here with this joint, basically the prismatic joint. Can you imagine that if this joint rotates, then this generates some centrifugal motion for this joint, the prismatic one, right? So when I rotate this very fast, you saw that this thing got extended, right? This is, I have to do it not too fast, not too slow. Come on. But that's basically it, right? When I rotate this one at some velocity, on any velocity, it generates some force pulling out this piece, right? So if this joint needs to stabilize this motion, then it has to counteract this torque, this force that is being generated. And this has to do with the velocity of rotations of all the joints, right? See, this joint affects other joints. And the other way around, like if this one is moving in some way, it also generates torques here. And it's the same thing with acceleration. That's more difficult to demonstrate. The point is that joints don't really move independently, right? So can we model them using independent controllers? Let's see. Let's have a look at a bit of the equations as well, so we get an idea of why joints don't move independently. So basically, this system of equations, if we expand it, it will be some equations of this form. So this would be the first row, which would be the first element from the D matrix times the first acceleration times the second element from the D matrix times the second acceleration, and so on and so forth. And then the first element of the C matrix times the first velocity, the second element times the second velocity, and so on and so forth, and the first element of the gravity term equals to the first torque, right? And equally the same for the second joint, basically taking the second row from all the matrices. Right, so this shows me basically for a given torque at a certain joint, what would be the accelerations and velocities for that joint. And what we see here is that basically we have dependence, let's say on the first equation, we have dependence on the velocities and accelerations and positions of the other joints as well, right? So here we have not just Q1 dot dot, but we have Q2 dot dot and Qn dot dot, right? So the accelerations of the other joints will affect the first joint. And the same thing with the velocities. And terms will appear here as well. So here's like all Q's, all the joint coordinates. So yeah, all positions will affect, or anyway, some of them. It's the same thing for the second joint, right? I have dependence of the first acceleration and the nth acceleration and velocities on the movement of the first joint. So joints do not really move independently, completely, right? As I'm trying to demonstrate here. However, we can still try to implement independent joint control as long as we have basically slow motions, right? Because there the effects of these accelerations and Coriolis terms are smaller. You saw when I do this movement basically slower, I don't have the prismatic joint jumping, right? So if I do slow movements or the masses are small, then we can, you know, simplify things a little bit as engineers, you know, we like to do. If we assume that the motions are slow, then we can kind of model the dependence of the other joints as disturbances, right? Because we always have disturbances anyway in the processes. So, you know, to some extent, the controller should be able to deal with these disturbances, right? And then, of course, we have to tune each controller very, very diligently. Okay? Let's see how could we actually tune controller for each joint. So we start from our dynamic model. That's the, you know, the model of the process. And since we're trying to develop a controller for each joint, we need an equation of motion for each joint. So basically we need a smaller dynamic model just focusing on this joint, and on each joint individually, right? Which is basically these equations here. The first, the second, nth equation. So if we start from those equations, it's inconvenient, I have to go back and forth. Basically, I can take all the terms that are not related to this joint, the first joint, and group them together and call them disturbance. Right? So I can write it like this for all the joints. Now, this is with indices. I have dii qi dot dot plus cii qi dot equals the torque of joint I minus all the other terms, which would be, let's write them down here just to have them on the same spot. So for the first joint I had d11 q1 dot dot plus d12 q2 dot dot let's take the two joint example that we have there as well. C11Q1 dot plus C12Q2 dot plus G of Q1 and Q2. There I had it with Q, which contains everything, but since there are only two, I'll write tau 1, and the second 2,1 Q1 dot dot plus D22 Q2 dot dot plus C21 Q1 dot plus C22 Q2 dot plus G. This should be 1, this should be 2, Q1 Q2 tau 2. So what I'm saying here is I will, for the first joint, I will neglect this one and this one and this one, right? I will not totally neglect them, but I will add them up and I will put them here as disturbance 1. And because they go on the other side, it will be with a minus. All right? Similarly, I should do this for these joints. So I take these 3 and call this W2. All right? That's the general form of the that I have there. So in the end, I have just the inertia part and the Coriolis part equals to the torque minus all these disturbances. Right? What I said earlier, as long as these velocities and accelerations are small, you know, I will end up with having small disturbances. Right? Good. Right. So how could I design a PD controller now? Let's take the PD controller for now. If I have such an equation, let's write it here as well. You remember how you designed, how you tuned equals I minus WI. You remember how you tuned controllers? Anyone? How you designed PID controllers? The Laplace? On what? On this equation?
It's not efficient. It is.
We can assume these are not changing. Assume, yes. Yes. Okay. But Laplace you apply on what?
We need the equation.
We need the
feedback.
feedback. We need the closed loop system, correct? All right, because this is the open loop system, right? I have some torque, it does something.
Process.
This is the process, yes, but I need to close the loop, write the closed loop form, and then apply Laplace. I'm not a control expert. I was hoping you would know better than me, but yeah, maybe on the next ones. So what would be the closed loop form? Basically, I have to say, okay, how do I calculate this tau I? Right? And basically, this is my controller output, the process input. So, you know, if I say I have a PD controller, so proportional derivative, then this would be what? It would be a gain, a proportional gain, times what?
We also have the
Kappa D multiplied with
Kappa P, the proportional part for now, right?
Kappa P multiplied with the parenthesis 1 plus D.
I'm not looking for this,
Over dt.
I think, no. Let's look at the diagram again.
The derivative of the error over time.
Almost. It's the proportional part. times what? Times the error, right? A, right? And if I have the d part, and it would be another gain kd times the derivative of the error over time. Okay, that's what I'm looking for. The general, basically this is this equation, right? That's what I said. I have the kp times the error plus kd times the derivative of the error. I add them together to calculate my action, my input, right? Which is the torque. Correct? Okay. So this is my input. And what is the error? Let's write on this side. Right, perfect. So I will have a q d I. So this is all with I. Right? I forgot to write this. And kpi, kdi, because I will have different gains for different joints. Right. Okay. So this is with I. So this is the desired, I think that's how I noted it, minus the actual. So this is what the set point, this is what I measure. Right. And the derivative of the error over time would be this divided by the time difference over dt, which then it would be this divided by the time difference, this divided by the time difference. So then in the end it will be dot, dot. So the joint velocity and the reference velocity. Okay. We'll assume, since we said especially that we have like fixed, not fixed, but slow motions, we will assume that this is 0. So we're talking about, I don't know, a step reference where the velocity is 0, so it doesn't change over time, not a varying thing, right? Just to keep things more manageable. If we replace this here and then eventually here, what will we get? dii qi dot dot. Let's do it step by step. Let me not break my back. So here I have kpi. This will be, oops, this part. qd minus qi, correct? Plus kdi, which this will be 0, so minus qi dot. All right? So if I replace this part with tau, I mean tau with this part, I will have C11 qi dot equals this whole thing. Kpi qdi, I'll remove the parenthesis for now because I want to group things. Qi minus qdi qi dot minus wi. So I just took this part and put it here. All right. And now I move this qi on this side and I factor it out. So I get dii qi dot dot plus C11 plus kdi. Qi dot. I also move the ki here. Mine plus kp iqi equals what? This part minus this part. So I have kpi reference minus wi. All right? Following? Good. I can also divide by kpi. So I have just KDI from here, but it makes little difference. So this is now my closed loop, the form with the feedback basically, right? So this now represents the system that I'm trying to tune the controller for, right? What order is this one? Second order. So let me jump on some slides. So basically, yeah, this is what we have here, considering this part. So this is second order system. So now I do Laplace on this one, right? And I end up with this form. I'm not going to write on the board. It's written there beautifully. And I basically, since I want to neglect the disturbances, I will neglect this part, right? Because it's disturbance, I cannot model them. I don't want to model them, right? That's what I'm trying to do, is say, okay, it's disturbances. Hopefully my controller will be good enough and will reject those disturbances, right? So basically I can take the characteristic of the system, which would be this part, right, and equate it to the general characteristic of a second order system, where I have these terms, the natural frequency and the damping of the system that I want. And based on this natural frequency and damping, I can basically calculate proper QPI and QDI. You remember these parts vaguely, right? Any questions on this part?
We should have a whiteboard a little bit to see the equation.
Sorry. That's something I need to improve on, real estate on the whiteboard. Okay, questions? No? Good. Now, we made some assumptions, and these are pretty strict assumptions, you know, that these velocities are slow and so on, but we don't want our robots to be slow, right? We want to do things fast. So independent joint control works, and you will see it also in the lab with a little robot, but it's not very efficient. And it's, you know, when we start moving faster, you know, these disturbances, they cannot be compensated anymore. So what happens when our assumptions are not met? We need a different approach. Basically, we need a MIMO kind of approach. But before we design a controller, we do a little trick. And I'll erase the board here so we can fill it up again. Because somebody doesn't erase their boards, and I cannot use both of them. Okay, so starting from the model, basically we said that, okay, if I want to design independent joint control, I choose my torques to have some values following the PD controller, PAD, or whatever controller I want to implement. I can do this for the whole vector of torques, right? So starting from this one, my chalk, can I choose something smarter that will basically linearize or G? Because somebody mentioned it, like, okay, we can do these kind of things as long as it's a linear process, which is not really linear, right? Can we kind of like linearize this process? What? Yeah, how?
I'm not really convinced, but I think yes.
I wouldn't be asking if not.
Where the system works.
It's their system linearization, so probably we should be able to do it, right? Yes. Okay, so we linearize in a equilibrium point. That's what you're saying, right? And then we,
Stable works.
yes. So that's one way to do system linearization on a specific equilibrium point. But we can do something better. we can basically choose our input torque. So this torque to be equal to basically something like this, plus can I do this? I control my torque, I put it whatever values I want. Right? I can say, okay, I want my torque to have, this is A. Just to keep it clear. Nobody stops me, right? So what happens if I put my torque equal to this?
C and G simplify.
C simplifies, G simplifies.
The acceleration.
Sorry? This also simplifies. So I end up with what? Closed loop form, right? So again, this is closed loop because I choose what the torque should be. And I choose it to have these values here.
But how we choose this, or it's purely instinctive how we choose the torque to be?
There's no trick here. I took a matrix that I know.
Yeah.
I took another matrix that I know. I took some velocities I'm measuring, positions I'm measuring, and I multiply all of this together to calculate the vector, right? And then I end up with this thing. And this is my favorite slide. It's like, what? All right. So what's the catch? Right? And it's why I insisted in the beginning to state that basically this part here is the model of the process, right? It's not the actual process. It has some errors there. It's not perfect knowledge of the robot. You know, all the masses might not be exactly where we think they are. Even more so, there's friction that we didn't model and other things that we didn't model. And it's a model, right? So basically what I'm doing is not exactly this, because here the actual, the actual process has a more complicated equation than this one, right? We assume it's this one. So if we assume it's this one and we choose the torque to have that value, we can simplify things. So again, we make some assumptions, as with the independent joint controller, that the velocity will be slow and so on. Now it's a different kind of assumption. It's an assumption that we know the model accurately, right? And as long as that assumption is good, so as long as these two are close to each other, then this linearization will work, right? And we have what we call system or feedback linearization or dynamic linearization, whatever. It's basically, we don't linearize what you were saying at a specific equilibrium point, we linearize at any point, right? Because we can linearize for any Q and Q dot here, right? But it's not necessarily a perfect linearization, right? So it will be a good linearization as long as the model is good, right? So basically what we're doing is we use knowledge of the model in order to linearize the real process. And again, as long as the model is good enough, then this will be a good linearization. All right, so we do basically something like this. We have like a feedback loop where we are measuring Q and Q dot, and we use the matrices that we measure. So V is basically C and G together, just to save space, we group them together. And as long as, you know, these represent the robot process, then this will be a good linearization. But the whole point is that now, if I have this feedback loop, I can, you know, control that already linearized system, right? Because now this is my process. And that's basically a double integrator, very more straightforward process to control. It's also purely linear, right? There's nothing unlinear happening here, so then we can do whatever we want to do. whatever linear controller we would like to do. One example that we use here is basically choosing this. Now A is my input and Q dot dot is the output, right? So now I have to choose this one because here I didn't put Q dot dot. If I would put Q dot dot, then I would have basically nothing moving, right? So I have some kind of another input and I'm trying to fit in there now my reference for the joins to follow and so on. So basically I can choose A to be something like this, where I have another feedback here with a Q and Q dot and R being the reference. The reference position and position basically. So if I use A up here, if I replace, then I will end up with this closed loop form, right, of the linearized system with some gains, kappa 1, kappa 0. And if I choose R to follow a trajectory over time, to basically follow a specific position, acceleration, and velocity, and I implement on this control, then I can end up having basically, zero tracking error or very good performance, right? And this is a MIMO controller, because this is basically state feedback, because I take where the states is positions and velocities, right? And I take all of them in one go. I have one matrix for all of them, and I control, the whole system, all the inputs and all the outputs at the same time. Of course, we can do other approaches, as you said earlier, right? Any MIMO controller. The whole point here is, this feedback linearization, like how can I get from this nonlinear system into a linear system, right? Again, this works as long as the modeling is correct. And you will try that in the lab. In the lab, we know exactly the model because it's in simulation, but you will introduce on purpose like mistakes in the modeling, and you will see that the controller basically starts misbehaving. While, when the model is perfect, the controller is perfect as well. All right. Any questions on this side? We have very little left, so shall we continue without a break, or you want to take a break? It's not really theory anymore, it's more like, Q&A. I would recommend continuing, but if you really want a break, we can take a break. You want a break? Okay. All right, so we keep on saying that we want to, we are controlling basically joint positions, right? But eventually we say that we want to control the end effector, right? So we still haven't solved that problem. How could we, implement, and even more than the position of the end effector, we might care about, joint velocities or end effector velocities. We're not going to talk about forces. Next week about that. All right. So how could we, start from this kind of scheme where we're controlling joint position? How could I adapt it so that we end up having end effector pose control? What would I need to change?
My reference and this is my output.
Okay. So what should be the new reference? Or I just change the reference and say here I have end effector pose?
No,
because we said we cannot do that, right? All right, so how do I do end effector pose control?
Maybe we can input the joint coordinates, calculate the motor kinematics, and at the end do the same, and then subtract them.
So at the end do the same. So here start with joint coordinates,
Yes,
forward kinematics, so I calculate end effector,
yes.
and then how do I pass that in the controller? What would be the error? So I take again end effector.
Yeah.
Wouldn't it be better to have the any vector coordinates, do inverse kinematics to find out the joint positions, and then put it together.
Right. So if we do what you were saying, right, we still, so what Matej is saying is, okay, I have joint coordinates. Matej, right?
Yes.
Okay, I think you heard that. Do the forward kinematics, end up with end effector pose, I don't know, some kind of transformation matrix or something, right? Calculate the error, and then feed that to the controller, and the input is what? It's still torques, right? Because that's what I'm talking to, right? And then you say, okay, I measure joint coordinates, and then do again forward kinematics here, right? F kine, and then take this thing basically and calculate the error.
Yes, but I do the same thing twice.
We cannot do
It's not
the first
the big
part
problem.
and inverse kinematics from the joint.
What's the problem with this one?
As Matej said, we do the same stuff
Twice. Okay. I mean, there's a bigger problem. Yeah.
That's not a problem. What's the problem? The control.
The control has to do what? Take some difference in pose and then figure out how that translates into joint torques.
The feedback is not good.
Because let's say, sorry, just to, let's say we have, target position here and we are a bit to the left. So we have basically a difference on the X axis. Everything else is okay, but we need to go a bit to the right, let's say, okay? So all the errors will be 0, and I will have 1, 0 that is 1, right? I have to decompose that error and figure out what joint has to move in what way to move a bit to the right, right? So the controller cannot do that, right?
I said an opinion about the feedback, which we need to be pulled before the second kine to be after the first.
So if the feedback is Q, joint coordinates, then the set point has also be joint coordinates. All right, which they have to have the same, they have to be the same thing. All right, you said something else.
Yeah, inverse kinematics.
Inverse kinematics where?
Before the reference point.
So I have a reference pose, right? And I decompose that into joint coordinates, right? And then I can do the same thing as we did before. If I really want, I could do, okay, actually I shouldn't have written this here, F kine. If I, sorry, this goes here. If I really want, I can, I don't know, do some kind of comparison here as well. But then what I should end up is like some difference in joint coordinates. So I still have to translate basically the difference in pose into difference of joint coordinates. We could do something like this with the Jacobian, because basically the difference of pose is difference of position, which is basically a differential of position, so basically velocity. So I could use the Jacobian maybe from this difference to calculate difference of joint positions, so basically an error for joint positions, but that's typically not what we do. We typically do this, right, without this feedback. We typically start with end effector pose, target pose. We decompose that to joint coordinates, and then we do the control at the joint level, right? As long as this is a good controller, and as long, of course, my inverse kinematics is correct, right, then I know for sure that, I will have reached the right target pose.
Without the FK.
Without the feedback. I don't need this.
Yes.
Theoretically and practically as well, right? Because this thing we can know with good accuracy. Right? We can model the forward kinematics good enough so that we know the inverse kinematics good enough then we can do this open loop. We don't have to really verify. We can verify as well, but also in order to verify, we'll need an extra sensor. It doesn't make sense to do it through this one, because if there is a problem, there will be something, I don't know, with the way the joints are reported, or something along those lines. All right. What if I want to control joint velocity? How do I convert a joint position controller to a joint velocity controller? How? Sorry?
Can we add a derivative block?
A derivative block for?
Like convert the joint positions to the velocities.
Yes. Where to add the block? Or
Right before the set point.
right before what?
I said right before the set point, but then we also need to not be before the feedback loop, but then we also need to add an integrative.
It's simpler than that. I can just basically say, okay, my set point is velocity and my response is velocity, because I can read joint velocities. Or if I cannot read, I can read joint positions and differentiate that. And then basically I can design the controller to basically get a set point and a reference in joint velocities. So that's as simple. I just put two dots and I'm done in theory.
And the same goes for acceleration.
Yes, the same goes for accelerations, right? If I want to control joint accelerations. But typically we want to control the end effector side. So how could I implement end effector velocity? This again starts from joint. So what do I need to do in order to control the end effector velocity? What blocks do I need? The Jacobian. Once again, sorry.
Yeah, the Jacobian can be calculated with the joint positions.
So where do I put it? The Jacobian makes sense because the Jacobian is giving me basically the relation between joint velocities and effector velocities, right? So where should I put it?
After the ADN,
Here.
because we have the position, the velocity.
And the velocity, okay. I can measure the velocity, let's say. And what do I get from this?
And effector.
I get the end effector velocity. Okay, but how do I control it? Xi. Sorry?
We can use the inverse Jacobian and
Okay, so this would be our feedback. You said, right? But using the end effector properties for feedback is always tricky. The same thing with the position, right? It's something I cannot measure directly. I can only measure indirectly, right? And then, okay, I have a reference Xi. Xi was the velocity, the end effector velocity, and I calculate some error. I still have to decompose this error if I feed it to the controller to joint torques, right? So I have to go back down to joint torques. How did we do it for the end effector pose? I started with pose and I calculated joint coordinates.
Yes, with the inverse. If we know the velocity of
The inverse.
vector, with the inverse Jacobian, we can see what the velocity.
So let's see. Exactly. So I do things at the beginning, not at the end. That's the message. So I have a Xi reference and I want to convert that to joint positions or velocities. We saw we can do joint velocities, right? So how do I go from Xi reference to joint velocities? Right, so this is the Jacobian equation, right? So if I take the inverse of the Jacobian, I calculate target velocities. So I take the Jacobian, the inverse of the Jacobian, and this gives me joint velocities. And then I can do the control at the joint velocities level. There is one thing missing though. What feedback?
Now I have to take joint velocity and transform the Jacobian into end effector feedback, end effector velocity.
All right, so I close the feedback here. My feedback is here because here is the controller. If I put another feedback, I need another controller, right? And I don't want to control at the end effector level, as we said. But again, I assume I know the Jacobian well enough, and that's a good assumption, right? So that I decompose the joint velocity, the end effector velocity to joint velocities, and then I control just here.
And that's all.
Sorry?
And that's all. We've done.
We're missing one thing. It's not really feedback. I need something here. The Jacobian is a function of position, right? So I need not really feedback, but I need to get back the position and update the Jacobian with a new position constantly.
And get from the process and
Yes, I measure it. So it's not really feedback because it's not a controller here, but I need to update the Jacobian because the Jacobian is a function of Q. So I have a Jacobian at this configuration, but the moment I start moving, the Jacobian has changed. So if I want to do, end effector velocity, I need to update the Jacobian to calculate the joint coordinates with the new Jacobian. There is a -1 missing here. But that's the idea. We take from the process Q, we feed it back to update the Jacobian. Any questions? So we finished in less than 2 hours.
Why did we take Q from the process?
Where to take it from?
It seems counterintuitive to take. Personally, I would have put an integrator after the.
Q dot. So integrate this one.
Yeah, I don't know.
I mean, if we have a sensor to measure it,
Okay.
we don't need to integrate. If we don't, then yeah, we can integrate, but integration, we know it's troublesome sometimes. You can have error accumulating and drifting and things like this.
But I know the position from the process.
Typically, we know the position of a joint. If we don't know it and we know the velocity only, then yeah, we should integrate that to get, because we need the new positions to update the Jacobian. Any questions?